So now let's do an example of a more complex circuit, of circuits that have multiple outputs. So here's an example. This is a priority circuit. The output is asserted corresponding to the most significant true input. So it's priority in that we have a input A3, A2, A1, and A0. So let's say this is the president of the university, and this is the dean, and this is the department chair, and this is the faculty member or the professor. And so the president gets highest priority. So A3 says, hey, you know what, if the president, let's say we're all trying to reserve a room to use, and the president says, hey, I need that room. Guess what? Guess who gets that room? The president has priority. But if the president doesn't need it, and the dean says, hey, I need that room, it doesn't matter what the chair and professor say, the dean gets that room. If, on the other hand, the president and the dean don't need the room, and the department chair says, hey, you know what, I need that room for my use, it doesn't really matter what the professor says, lowest priority, the department chair gets it. On the other hand, no one else needs the room, and the professor says, hey, I want to use that room, the professor gets to use that room. So we have this priority circuit that's going to say who gets to use the room. So the outputs, Y3 to Y0, indicate who gets the use of the room. If Y3 is 1, it means that the president got to use the room because the president has priority. If Y2 is true, and all the other ones are false, the dean gets to use the room. Okay, so we have this priority circuit, and we can see now what the outputs should be. So we have a truth table. We have our 4 inputs, A3 through A0. And again, we could write that as A subscript 3:0 as a shorthand. Or we can write it as I've shown here, A sub 3, A sub 2, A sub 1, A sub 0. These are just like regular signals, but they have a grouping. So they're grouped together. They have an association. So we put that subscript. But this is the same as the input variables that we've been using up until now, A, B, C, and D, for example. So just 4 different inputs. And so now we can figure out, well, what's the output depending on what the combination of the inputs is. So this differs from what we've done up until now. Right now, we have our 4 outputs shown on the same truth table. So we have Y3, Y2, Y1, and Y0. We could write 4 different truth tables. So we have a truth table for Y3, and then I could write a different truth table for Y2, and then I could write a different truth table for Y1, and a different truth table for Y0. And well, not only does that waste my time, but it really makes it even more complex because there's some relationship between these outputs that I miss when I write it on separate truth tables. But logically, it's as if I'm writing 4 separate truth tables. These outputs are independent and determined completely by what the input combination is. Okay, so let's figure out how to fill in this truth table. So we want to figure out what the outputs are given each combination. Well, let's see. When A3 is 1, says the president, input A3 wants to have the room. And so, guess what? That president, that person, that highest priority person gets the room. So when A3 is 1, Y3 is 1, and guess what? Nobody else gets it. 0, ... All of these lower priority inputs where individuals don't get it. Okay, so that's cool. When the president wants it, wants to get that, reserve that room, the president gets that room. But what about when the president doesn't want the room? Well, when the president doesn't want the room and the next priority person, in this case the dean, wants the room, so there's a 1 on that input saying, hey, I want to reserve that room, guess who gets it? Well, the dean's going to be able to get that room. 1, 1, 1, 1. The dean gets the room. Well, the president didn't want it, so the president didn't get it. Dean got it, and the lower priority individuals or inputs, they may have wanted it, but guess what? So in this case, the professor is saying, hey, I want that room too. Out of luck, you don't get it. Where the chair says, hey, I really want that room, out of luck, doesn't get it. Or both the chair and the professor, those two lower priority individuals say, hey, we both want that room, I want that room. Nope, you don't get it. The dean already requested it and got it. He has highest priority, or higher priority than you. So now we can look at the case where neither the president or the dean, the two highest priority inputs, A3 and A2, wanted the room or requested the room. They said, hey, yeah, we don't need that. And in this case, the chair, A1, says, yeah, I want that room. Guess who gets it? The chair gets the room. The dean and the president didn't want it anyway, but even when the professor, that lowest priority input, requests it, doesn't matter. The chair already requested it, you don't get it. Okay, the last two cases where, well, the higher priority individuals did not request the room, and the professor requests it. That lowest priority input, A sub 0, guess what? Professor finally gets to use the room. Nobody else wanted it, they don't get it. And then the last case where, well, no one wants it, and no one gets to use the room because no one wanted to. Okay, so we have now a truth table for our circuit that we'd like to build. Right now we just have the inputs and the outputs, the interface, and we have a kind of black box, a circuit in here that we say, hey, make sure you do this function somehow. Well, now let's dive in a level of abstraction and figure out, okay, well, how do we build this circuit? Well, let's see, is there any way we can look at this? Well, if we look at that, Y3, and we look at these outputs independently. So just ignore Y2, Y1, and Y0 to start with, and just look at Y3. So the Y3 output is true when A3 is true. If we look at these two columns, in fact, yeah, those are identical. So Y3 is just A3. So if I want to build a circuit for that, here we go. We have our inputs on the left, A3. That goes directly to the output. If A3 is 1, it doesn't even matter what the other inputs say. The president gets that room. Y3 is 1. Well, maybe we'll look at these cases here where Y2 is 1. I could use sum of products and then minimize it using either K-maps or Boolean theorems. That's one thing we could do. So that would be pretty easy, especially with K-maps. But I can also kind of see by inspection, well, Y2 is going to be 1 when A3 is 0 and A2 is 1. So when A3 is 0 and A2 is 1, then we're going to get Y2 to assert. Similarly, we can see that Y1 is going to assert when A3 and A2 are 0 and A1 is true. So now we have A3 bar, A2 bar, and A1. Then we'll get Y1 to assert. And Y0 is going to assert, well, I can immediately use my sum of products, my min term there, and get Well, y0 is going to be A3 bar, A2 bar, A1 bar, and A0. So A3 bar, A2 bar, A1 bar, and A0. So A3 bar, A2 bar, A1 bar, and A0. And we already did put this into our circuit form, into gates of our function. And you can notice that we can include these complex gates. So, for example, instead of writing this gate with an inverter, we could write the gate shown here. It's equivalent to AND body with a bubble on one of the inputs, and so forth for these other gates. This gate, this gate. So we can actually also write the truth table so that it indicates this function more clearly. So we kind of said this in words too. So if we have our inputs A3, A2, A1, and A0, and again our outputs Y3, Y2, Y1, and Y0, and we write a truth table for that, we can see that, well, if we have 1 on A3, it doesn't matter what A2, A1, and A0 are. And so we can use the don't care symbol, or X symbol, which is a don't care, on the input as well. So we say, in this case, if A3 is 1, doesn't matter what A2, A1, and A0 are. These are don't cares. No matter what, Y3 is going to be 1 if A3 is 1. So we basically collapsed these 8 rows of a table into a single row of the table. Now we can go to the next rows, and we can say, well, if A3 is 0 and A2 is 1, doesn't matter what A1 and A0 are, Y2 is going to get the room or the requested item. So A2 has priority over A1 and A0. So now we've taken these 4 rows and collapsed them into a single row. And moving forward, if A3 doesn't request the room, A2 doesn't make the request, but A1 does make the request, it doesn't matter what A0 does, A1 will get the room. So now we've collapsed these 2 rows into a single row, and the remaining 2 rows can't be collapsed, can't collapse anything smaller than 1 row. So if nobody else requests it except A0, A0 gets the requested item, in our example before, the room, and the top row, when nobody makes a request, nobody gets the room, also moves over to this truth table. So we can have don't cares on the inputs as well, where, for example, let's review this. If A3 requests the room, if A3 is high, doesn't matter what the other inputs are. No matter what the other inputs are, if A3 is 1, Y1 is 1. And the remaining outputs are 0, and vice versa. So using don't cares on the inputs, we can collapse the truth table into a more concise truth table, and we can really tell what the output equations are more easily. So if we consider the Y3 column, well, we have a single 1 there. Y3 is going to be A3. The inputs A2, A1, and A0 are don't cares. Similarly, we can see that Y2 is A3 bar, this 0 there, and A2. The remaining input variables are don't cares. Y1 is A3 bar, A2 bar, A1, and finally Y0 is A3 bar, A2 bar, A1 bar, A0. And so we end up with the same result as when we analyze this larger truth table, either by inspection or more kind of methodically by putting it into a key map. But this more concise truth table is a lot easier to understand and also easier to figure out what those output equations are.